Hi everyone, Dr. Waite here. We are going to have a recorded class meeting for Civil Engineering 331 today. As you have seen via email, the university is closed due to inclement weather. So hopefully you're staying warm and keeping off the roads. Here's a photo of what my driveway looks like at the moment, so it's definitely snowy out there. Let's go through the announcements before we get into the material. Your homework assignment is on track for the same due date as before. So homework 2 will be due on Wednesday of next week. And I'll go through a couple of examples in this lecture that I think will be useful to you. And I also intend to send an email that has a spreadsheet file related to the pipe sizing example from this lecture. So that's what we're going to go through today in this recorded class meeting. It has the remainder of the pipe diameter example using Microsoft Excel, and then I'm going to introduce a couple of other less accurate ways of measuring pipe friction and the effects of that on energy loss, the Hazen Williams equation and the Manning's equation. So the Darcy-Weisbach equation is the gold standard, but it sometimes is a bit complicated, and so there are more streamlined and fairly effective methods, and we'll get into all of that.
Last time, we had this conundrum. The problem was we're trying to figure out how big should the pipe be. You know, we want to make sure there's enough pressure downstream. So you want to have a big pipe to deliver lots of pressure downstream, but you want to have the pipe be as small as possible to save money. And so the conundrum, the thing that we were trying to get through was the fact that you don't really know the friction factor until you know the pipe diameter, because friction factor depends on pipe diameter and velocity, which is itself dictated by pipe diameter. So we don't know the F value because we don't know D, and we can't calculate D until we know the F value. So we had all these flow characteristics, the roughness of the pipe, the amount of head loss, but the challenge was D depends on F and F depends on D. And so our way around that problem was we started with an initial guess. And we calculated what the diameter would be based on a guess of the friction factor. And then we did subsequent iterations to try and improve on our guess of the friction factor. And that's where we left off. So let me bring up the spreadsheet template that we had started with. And let's just start here at the top and briefly revisit what we knew. These constants that aren't changing are things like the flow rate, the equivalent sand roughness for the pipe, the length of the pipe, gravitational acceleration, the amount of head loss that's tolerable, and the kinematic viscosity. So we started off with just some guess of the F value, and from this given formula, which relates diameter to all these factors, including the friction factor, we found out that the pipe diameter that's needed for this F value would be 0.1395 meters. And so if you know the diameter, then you can calculate the area, the velocity, the Reynolds number. And with the Reynolds number, we were able to calculate an improved guess of what the friction factor would be using, what's the name of this equation? Jane. Yeah. How do we know it's Jane and not Colebrook?
They look different.
They look different. Yeah, specifically, why do we like Jane, and what makes it easier to use compared to the Colebrook equation? It's not implicit, that the F value is not on both sides of the equation. So it's much simpler for us to use. So yeah, this is the Jane equation, the one that we can calculate F directly as long as we know the relative roughness and the Reynolds number. So we now have an estimate of the Reynolds number, and we always knew the equivalent sand roughness, K sub S, and based on some assumed diameter that we're going to be calculating, we have an updated F value. And it changed a lot from our initial guess. So this big difference tells us that we probably need to do another iteration. So there's certain things in our calculations that are constant, like the flow rate is constant, the length of the pipe is constant, you know, all these parameters at the top are constant. But to avoid having to type the equation over and over again, what I'm going to do is I'm just going to copy and paste. So my formula here for the diameter, when I copy and paste some of the references up to the top factors, which are constants, those were anchored, but there's a relative roughness, a relative reference here to the F value, so that when I pasted this formula for D in iteration 2, if we look at the formula for that, all of the constants, it's still looking up at the top, but now it's looking at my new guess F value, which was the end, the output of the first iteration. So this is a better guess of the diameter. And so now with this better guess of the diameter, we calculate what's the velocity with this new pipe size. And with a new velocity comes a new Reynolds number. And then that enables us to calculate an improved F value. So here's the formula for the F value. I don't really need the formula because I'm just going to end up pasting the equation from before. So we have a new F value. Let's find out how much did it change in this iteration. So from this beginning F value within the iteration to the ending F value at the output of the iteration, the difference is the final value minus the initial value divided by the final value times 100. So hopefully the change is getting smaller, and it is. There's a 5% difference, whereas in our previous iteration there was a 65% difference. And so that's an indicator that the solution is stabilizing. It's beginning to converge. That's great. So now at the input of iteration 3, we're just going to use the output F value from iteration 2. And now, rather than typing the formula for D, I'm just going to go up here to my equation for D, and I'm going to press Control-C to copy, and down here I'm going to press Control-V to paste. So the diameter changed a little bit. It went from 0.1725, and now it says 0.1707, so it's making less drastic changes as well. So let me copy all of these factors because I want to compute a new updated Reynolds number. So just the formulas from the previous iteration, I can Control-C to copy. When I get into the location I want to paste those formulas, Control-V, and it pastes. And then with an updated Reynolds number and the new diameter, I'm going to have it calculate another version of the friction factor. So let me just copy the formula here from the previous iteration, Control-C, Control-V. The F value is not changing much at all now. It went from 0.0219 to 0.0220. And as a percentage, that is, if I find the percent difference here, I guess I could paste that as well, but now it's just changed 0.26%. It's probably okay for us to stop iterations once the F value stabilizes to 1% or better. So we're already better than that. We're below 1% change. So that tells us that the solution has converged. And just to illustrate that the solution is converged, what if we did this one last time? And let's see how does the diameter change if we adjust it one last time. So now, with this most recent F value, let's do it again by pasting the formula for D, Control-C, down in here, Control-V. The diameter didn't change. It went from 0.1707 to 0.1707. So both the F value has converged from the input to the output within an iteration, and the diameter has also stabilized. So with both of those converged on the answer, we can say that the diameter that this should be built is 0.1707 meters. Now, there's probably not a commercial pipe that's exactly that size. So what should we do if we want to make sure that we can achieve 300 liters per second and we can afford to have 45 meters of head loss? So think about the commercial pipe sizes. If it's saying use 0.1707, there might be a pipe that's 0.15. There might be a pipe that's 0.175. There might be a pipe that's 0.2. Should we round up or round down? Up. You're right. Why should we round up?
Does that have also to do with the pipe friction? Pipe friction is greater for a smaller.
There's more pipe friction. There's going to be more energy loss for a smaller pipe. Or another way to look at it is if we rounded down, so if we made it, this is saying it has to be at least 0.17 meters. If we made it 0.15 and all we had was 45 meters of head to push the water through that pipe, we wouldn't be able to achieve 300 liters per second. Water would still flow, it just wouldn't hit that target flow rate that we're trying to get. So the pipe would be inadequate. All right, so any questions about this example? I'd recommend that you save this template. I think that you can use it on the last homework, the last problem on the homework. You can do the calculations by hand if you choose, or you can use the spreadsheet. If you use the spreadsheet on the homework, then be sure that you upload the spreadsheet file. But then also on the paper, you need to write down what your answer was. And so don't just like totally neglect putting anything on paper because you've used Excel. You need to, on the problem, I don't remember if it's problem 6, I don't remember the number, but you'd basically summarize the unknown and then you'd say solve this on Excel, final answer equals whatever. All right. Okay, well good. So that's the accurate way to calculate the pipe diameter. There is a so-called easy way where there's an empirical equation that allows us to estimate the pipe diameter that's needed. And here's that equation. It's less accurate, though, than the spreadsheet method that we've just gone through together. This explicit empirical formula will get you to within about 5%, and it's valid within a pretty wide range. But the tricky thing in using this is, number one, avoiding making a mistake, because if you look, you've got flow rate to some power, a ratio to a power, and then all of it to another power. In my past experience, when we do this same example, but with this formula, more than half the class will make a mistake just putting it into their calculator. So, I suppose it's easier than setting up a spreadsheet, but it's risky because of input errors that can be made, and also getting the units right. In this equation, if you accidentally put in millimeters to K sub s, when really here down at the bottom it says it needs to be in units of meters, then that's also going to give you the wrong answer, even if you put the numbers into the equation in the right spot. So I wanted to mention that there is a formula indicated in the book, and there it is. So we've just been talking about the Darcy-Weisbach equation. It's the gold standard. It's the most accurate way of estimating head loss due to pipe friction. It's the most flexible because you could use it for water, but you can also use it for other liquids as well, like seawater or oil or alcohol, honey, whatever you've got flowing through a pipeline. The Darcy-Weisbach equation can estimate the head loss due to pipe friction as long as you know things like kinematic viscosity of the fluid, as long as you're able to characterize the F value, which itself is going to depend on pipe diameter, equivalent sand roughness, and so on. So it's the most accurate, but because F is iterative, it requires a little more work. You're going to use design software this semester. In maybe a month, I'll encourage you to download Bentley Water Gems. In around a month is when we're going to start using it. And the nice thing about Water Gems is it does the Darcy-Weisbach equation, and we don't care if it takes the computer 0.2 seconds instead of 0.1 seconds to do the calculations, because it can do them really quickly. It's a little bit cumbersome for us to calculate the friction factor if we're doing it on paper, but it doesn't slow the computer down one bit. And so there's really no reason not to use this most accurate friction factor equation if you've decided to use some design software for your calculations. If, however, you're doing hand calculations or you're out in the field and you need to estimate head loss due to pipe friction, then the Hazen Williams equation is a good compromise. And a lot of designs have been, in the past, based on the Hazen Williams equation because it hasn't always been as easy as we've got it now to estimate the F value. That was a considerable numerical challenge for people 20, 30 years ago. So they use these easier methods that aren't as accurate, but they have fixed roughness coefficients that don't depend on the flow conditions. So the Hazen Williams equation has a narrow range of pipe diameters that it works for, 50 millimeters to 1850 millimeters. That limitation doesn't apply to Darcy-Weisbach. Darcy-Weisbach is accurate for very tiny flow channels up to enormously large flow channels, but Hazen Williams has this range that it's been calibrated for, and it's only truly valid at water temperature of 16 degrees Celsius and for velocities less than 3 meters per second. So if your water is any temperature other than 16 degrees Celsius, the Hazen Williams equation is going to have a little bit of error built in because it has a fixed estimate of what the fluid viscosity is. So it's assuming water at a given temperature because the roughness coefficient has just, to simplify things, picked kind of a middle of the range value. So here is the Hazen Williams equation, both for SI units and for British gravitational units. And if you look through our textbook or through the FE reference manual, you'll notice that there's two basic versions of the formula. One version of the formula you would use to calculate the velocity of water flowing through a pipe if you know the slope of the energy grade line. So S sub F, the slope of the energy grade line, is how much head loss due to pipe friction there is in a given length of pipe. So H sub F divided by L is the slope of the energy grade line. So if you know the slope of the energy grade line, the hydraulic radius, and then this friction factor, C sub H, you just look up a friction factor based on what the pipe is made out of, and then that would tell you the velocity of water as it flows through the pipe. So if you wanted to know the flow rate, what would you need to do with the Hazen Williams equation if you want Q instead of V? Multiply by area. That's exactly right. So you could say that the Hazen Williams equation technically only calculates the velocity, but we can calculate the flow rate just simply by finding the cross-sectional area of the pipe, and if you know the velocity of the water and you know the area, which is for a circular pipe pi d squared divided by 4, then the flow rate is area times velocity. So you can use the Hazen Williams equation to calculate flow rate for a certain slope of the energy grade line, or if you know the flow conditions, like if the velocity or the flow rate is known, then you can use the Hazen Williams equation to estimate how much energy loss there is. So solving for H sub F. So we've just rearranged the equation in this bottom one after substituting in, here in S sub F, we substituted in H sub F divided by L. So that's how these two equations are related. And the British gravitational formula of it is just because we have different conversions rather than meters of length. Of course, we'd use feet for the length. And the C values are equivalent. There's not a different C value table whether you're going to use SI or BG units. The C values are constant and interchangeable between versions of the equation. All right, so Hazen Williams, it's easier to use because we don't have to fuss around with the friction factor. We just look it up off of a table. Now let's get some practice applying the Hazen Williams equation. Let's say that we've got water starting in a tank. So it's flowing through a pipe to a spigot, and it's flowing through cast iron pipe. And so we go to some table and we find out that the Hazen Williams friction factor C is 130 for cast iron. Now here we've got a specified unit weight of water of 9790 newtons per meter cubed. We're accustomed to seeing the unit weight being 9810. That's the unit weight of water at 4 degrees Celsius. But as water gets warmer, its density goes down. And so does the unit weight accordingly. So this is the unit weight of water at maybe 20 degrees Celsius. So it's flowing through 760 meters of cast iron pipe, and we want to find out what's the pressure downstream. What's the pressure at this downstream location? So we're going to use both the energy equation and also the Hazen Williams equation. So the first step here is to use the Hazen Williams equation and calculate what is H sub F. So I'm going to pause from talking, give you and your classmates a chance to calculate what is H sub F using the Hazen Williams equation, and then we'll talk together about how to substitute that into the energy equation and what I mean about velocity head being negligible. Okay, so for now, calculate H sub F. This example. All right, so the formula is going to need us to put in the length, the diameter, the C sub H value, and the velocity. We've got everything already except the velocity. We're going to have to calculate the velocity. We've got the flow rate, and we know the pipe diameter. So, oh, where is it? Oh, there it is. For a second, I was worried I hadn't given you the pipe diameter, but there it is. It's 100 millimeters. All right. So from the pipe diameter, we can calculate the cross-sectional area. So here I've done that. It's 7.854 times 10 to the minus third square meters. And so then with the flow rate converted from liters to cubic meters, and the area, it works out to 1.40 meters per second. So that's the velocity. Now we can put that and the length and diameter, which we already knew, into the Hazen Williams equation. We get that there's 17.54 meters of head. So that's how much energy is lost as the water's flowing through the pipe. So let me next write the energy equation on the whiteboard, and then we'll go through the process of analyzing which terms get canceled out and which terms don't. Okay, I've written the energy equation on the whiteboard. Now let's look at the diagram here. Location 1 is going to be in the tank. And what I mean specifically is location 1 is going to be here in the tank where it's in contact with the air. So 1 is at the surface of the reservoir. So what's the pressure at location 1? It's 0 gauge, or we could say it's atmospheric pressure, which if this is at sea level would be 101 kilopascals. But let's just work in gauge terms. So P1 is 0, so that allows us to cancel out that term. Location 2 is going to be at the spigot where the water's coming out, and we'll just choose location 2 to be once the water comes out of the spigot. So it's not pressurized either. And so we can cancel out P2 because the water is atmospheric just at the junction of the pipe and the spigot. Hold on a second. No, we're solving what is the water pressure. So let's, instead of doing that, let's go inside there. Let's do it just before the water comes out, because P2 is what we're trying to find. Don't want to cancel that out. Yeah, what is the water pressure? So location 1, the elevation here, Z1, is 103.5 meters, and location 2, the elevation is 55 meters, and so Z2 is 55 meters. And it says here, assume that the velocity head is negligible. at the very end of the example, I'll show you why it's okay for us to make that assumption. But here at location 1, the velocity head's definitely negligible. Like at most, the water levels may be coming down very slowly if we're draining this tank. If the tank is being refilled, then the water level is staying constant. But the point is that inside of a tank, the water level isn't changing much at all. So we can feel perfectly justified canceling out Z1. But at location 2, the water is flowing through the pipe. What I'm going to show you at the very end of this example is that it's flowing slowly enough that this term is going to be basically negligible. So we could leave it in if we wanted to, because we know what the velocity is. The velocity is 1.4 meters per second. But you'll see in a lot of problems like this, they say, just for simplicity, go ahead and cancel out the velocity head terms because they count so little. So what we're left with is, oh, there's no pump either. So we know the elevation at 1. We know Z1 is equal to P2 divided by gamma plus Z2 plus H sub f, because we've canceled out the pressure head at 1, we've canceled out the velocity head terms, and if we rearrange that, because we're trying to find out the pressure inside the pipe just before the water goes out, then we could rearrange this to be that P2 is gamma times Z1 minus Z2 minus H sub f. Okay, so we know all of these things. We know that, for example, that the unit weight is 9790. We know the elevation at 1, the elevation at 2, and the magnitude of the head loss that's occurred as the water flows through the pipe, because we calculated that that was 17.54 meters. And so let me show you the rest of these calculations. So we rearrange the energy equation to solve for P2. And after we had water elevated up to 103.5 meters, it's flowing to a location where the elevation is 55, and they lost 17.5 meters of head as it's flowing through the pipe. So there's 30.96 meters of head remaining just before the water flows out of the spigot. And so therefore, the pressure at that location, which is going to be reflective of how much pressure is in the pipe due to the elevated tank at 1, it's going to have 303 kilopascals. So now, as to the question of whether it's appropriate for us to neglect the velocity head, let's just check that this one time, and then I think you'll feel pretty comfortable with us neglecting velocity head in the future occasions. So the velocity head, V2 divided by 2g, the velocity is 1.4 meters per second. If you square that and divide it by 2g, then you get that the velocity head is 0.0999 meters. And so then if you multiply that by gamma, so if you wanted to turn it from a velocity head into how much pressure would actually be accounted for by the speed of the water as it's flowing through the pipe. So this velocity head multiplied by 9790 newtons per meter cubed is equivalent to a pressure of about 0.98 kilopascals. So if we had accounted for the velocity head, then the pressure wouldn't have been 303 kilopascals, it would have been 302 kilopascals. So it's less than 1% of an effect, less than 1/3% of an effect if we go ahead and neglect velocity head in occasions like this. So just to kind of take a step back and revisit the broad strokes of this example. We're trying to find the pressure just before the water comes out of the spigot. And What was unique about this example compared to what we've done in the past is this time, instead of using the Jane equation and then the Darcy-Weisbach equation to estimate the effective head loss, we calculated head loss based on the Hazen Williams equation. So we could go back and solve this example again with Darcy-Weisbach and just kind of see how they compare. And we'll do that in some future class. We'll kind of compare a few different methods to get an idea of, you know, this gold standard of Darcy-Weisbach and how close does Hazen Williams get and how close do some other methods get. But are there any questions on this example before we move on to the last one? Yeah.
How does the units work for the Hazen Williams equation?
Ah, that's a really good question. I'm glad that you asked that, because you're wondering, like, diameter to the 1.17 power, and then this ratio of velocity to a unitless friction factor to the 1.85 power. How does all of that end up being meters on the left-hand side? That's a good question. The way that it works out is that this is not a dimensionally homogeneous equation. This is an empirical equation where just someone did a lot of observations in the lab and said, oh, it fits pretty good, you know? And so it's not dimensionally homogeneous. So the left-hand side units of meters you would not get by doing a units analysis on what's on the right-hand side of the equation. This is just an estimation. So thanks for asking that. Are there other questions? All right. So now what about this one? Same picture, same pipeline, but this is the other version of the Hazen Williams equation. Remember that there's two. There's one where we solve for how much head loss there is. That's what we just did. So we solved for the head loss. And then there's the other one where you can solve for flow rate when you know the amount of head loss that is available. And so now in this example, we're, instead of being inside the pipe, which we were on the first example, this is the one where we're actually looking at location 2 is just the jet as the water comes out. So the significance of that, the significance of location 2 being just outside of the pipe, is it tells us what the H sub F is. We're just going to look at, you know, how was the energy used? What happened to the energy between location 1 and location 2? So in this, location 1 is still in the tank. Location 2, we moved slightly to, it's just outside of the spigot. And so if you look at the energy equation, again, we're going to neglect velocity heads. So P1 divided by gamma plus Z1 plus V1 squared divided by 2G plus H sub P, which there's no pump, but we'll still just write it. Z2 plus V2 squared divided by 2G plus H sub F. All right. We're talking about an open tank of water, so that's why we cancel out P1. The water is exiting at that spigot, and so now we're going to cancel out P2 as well, because as soon as a water jet comes out of a pressurized pipe, it suddenly loses all of the pressure. The velocity at 1 is 0 because it's in that tank, and this is telling us to neglect the velocity head at 2. Even though the water is moving, it's such a small effect that we're going to neglect V2. And so there's no pump here. And what that tells us is H sub F is Z1 minus Z2. So all of the energy that was in the water inside of this tank is exerted by the time it gets out to the pipe. So we are going to try and calculate the free flow rate, like how quickly can the water get through the conduit if it's using all of that elevation to drive the flow. So H sub F, the head loss due to pipe friction, you just think about it, that's the energy that you're using to move the water. And the energy you've got available is the elevation difference. And so how fast can the water move in that case? This is the formula that you're going to use. And keep in mind this definition of slope of the energy grade line. I'll make that even a little bit bigger because it's important for this one. Slope of the energy grade line is calculated by H sub F divided by L. Okay, so the solution's up on the screen. We found that the delta Z, the change in elevation, is what's driving the water through that pipe. So the slope of the energy grade line is going to be the elevation difference divided by the length of the pipe. So the slope of the energy grade line. And since this is a circular pipe that's flowing full, we can use that shortcut for calculating the hydraulic radius, where it's just the diameter divided by 4. You don't have to use that shortcut. You could have calculated the hydraulic radius the old-fashioned way, and you get the same thing. But then when we substitute in the slope of the energy grade line, hydraulic radius, our friction factor for the Hazen Williams equation, and then this units conversion prefix here, then we get that the velocity is going to be 2.444 meters per second. That'll be the speed that the water's flowing through the channel, and we want to know the flow rate, so we have to multiply that by the cross-sectional area for the pipe. So it's going to go about 19.2 liters per second. If there's no valve, it's just wide open, full throttle flow. 19.2 liters per second. So if you wanted more flow rate than that, you can either raise the tank at location 1, you can lower the spigot at location 2, or you could find a smoother pipe, which would experience less head loss, or you could increase the diameter of the pipe. Any one of those 4 changes would increase the flow rate. Before we go, let's just take a look at Manning's equation. We're talking about empirical formulas that have been developed to estimate energy loss, and Manning's equation is mainly used for open channel flow, but in theory we can use it for closed conduit flow. It's just not at all accurate for closed conduit flow. Normally we'd apply it to, let's say, a trapezoidal open channel, but the same geometric parameters that apply to an open channel could be applied to a circular conduit where either it's flowing full or flowing partly full. Partly full circular sewer pipes are kind of a challenging numerical problem. We'll get to at the very end of the semester. We'll get into the geometry of a pipe that's flowing partly full. Manning's equation is used in those situations, but instead of a C value like we had for Hazen Williams, Manning's equation has an N value, an N friction factor. So here's a table of some typical roughness coefficients. You can see both the Hazen Williams and the N values for a variety of different materials. Now that's it for today. We are out of time, remember.